There's one more thing we want to talk about before we leave this section behind, and that's evaluating limits by changing to polar coordinates. Now, this is actually related to the second topic, which is finite limits. I mentioned in here that sometimes you have to use algebra pre-calculus to find that limit. So that might mean factoring and rationalizing, multiplying by a value, but it could also mean switching to polar coordinates. After all, we learned about trigonometry and all of that in pre-calculus. So switching to polar coordinates may be helpful. And that's exactly what we're going to do on the particular problem we're looking at right here. Now, before we do that, just remember that in polar form, in polar coordinates, these three theorems, identities are true, which that x is equal to r sine or r cosine theta, y is equal to r sine theta, and x squared plus y squared equals r squared. Okay, so they're asking us on this problem to find this limit. And they're not saying don't find that it doesn't exist, right? Because it does. We're actually going to prove that. So what they really want us to show is that there is a limit. Now see, the path method that we've been using doesn't really work. So if you approach on a path, you're going to get some value, right? But every path you approach on, so if I tried, path 1, and I said, hey, let's try that x-axis again, right, which is y equals 0. And then I said, okay, I'm going to find the limit as x goes to 0 of, and I put 0 in here everywhere. So x squared plus 0 squared plus x squared times 0 squared over x squared plus 0 squared. Sure enough, let's see, I'm going to get x squared over x squared, which is the limit of, as x goes to 0, of 1. So that's 1. But the problem is that this isn't going to prove that it exists. So every path that I try would give me that same value. It's going to give me 1. But the path method can't prove that the limit exists. It can only prove that the limit doesn't exist. So following lots of paths isn't going to help me here. So let me make a note of that. All right, so in other words, the path method isn't going to help us here. We can't prove that this limit doesn't exist. And as a matter of fact, any time you try, any path you try, it appears like it's going to be 1, right? If you try x equals y, if you try y equals negative x, if you try, x equals 0, it seems to always be giving 1, but that can't prove it. That alone is not enough. So we need to try something else. Instead, what we're going to try to do is we're going to convert to polar coordinates. Because algebra isn't going to help us with this. It's not going to factor nicely. It's going to be brutal. So we're going to convert to polar coordinates. We are going to take the limit. All right, now let's think about this. If we're approaching the origin, what that means is that r is going to 0. So we're going to let the limit as r goes to 0. So if you think about what this is doing, it's sweeping in closer and closer and tighter around that origin. So we're letting that happen. Now x squared plus y squared is r squared. So that's r squared plus, and then x is r cosine theta squared, and then r sine theta squared over x squared plus y squared, which is r squared. Now at first it might not seem like you've helped yourself, but you actually have. So let me show you. So this is the limit as r goes to 0 of r squared plus, and then this is r squared times r squared, which is r to the 4th cosine squared theta sine squared theta over r squared. Now these terms in the numerator both have an r squared in them, right? So we can factor an r squared out. So this is the limit as r goes to 0 of, sorry, that my r looked strange there, limit as r goes to 0 of, I'm going to factor r squared out. That leaves me a 1 plus r squared times cosine squared theta sine squared theta over r squared. All right, well, the r squareds are multiplied now, so they will divide away and make 1. And that leaves me the limit as r goes to 0. Messed up my r again. I keep making it look like an h, which is not my intention. All right, r goes to 0 of 1 plus r squared cosine squared theta sine squared theta over 1, which is nothing. Now, where is this going? As we approach 0, the angles are rotating all around, and it doesn't really matter because this is going to be 0. So this is 1 plus 0 times some number that we don't care about, which is 1. All right, so we couldn't prove that the limit exists in our standard factoring algebra way, like it wasn't going to work out. And we couldn't prove it didn't exist with the path method. So our next option was to convert it to polar, and that worked out. And we were able to prove that the limit exists, and we didn't need paths or anything like that, right? What we're doing is changing our coordinate system, and because of the properties of that new coordinate system, things worked out nicely in a way that they would not have worked out nicely if I tried to use just straight algebra on this original problem. It would have been pretty brutal. But down here, it worked out nicely. And so that option is always available to us if it's appropriate for the particular problem that you're in to try and see if you can prove that the limit exists that way.